Vectors is not in any way, at least not how we're going to cover it in this class, a complicated topic. A vector is a directed line segment. Okay, it's just it's a line segment with an arrow on it. It's a very simple concept. But it allows you to model things like wind speed or acceleration, force due to gravity. Vectors allow you to model quantities that have both a direction and a quantity. Okay? You know, for example, if you're talking about the speed of the wind, it's not interesting to know, if you just say, oh, the wind's blowing at 5 miles an hour. Okay, cool. But I'd kind of like to know which way it's blowing as well. Okay, so you can draw, to model wind speed, you can draw me a bunch of arrows pointing to the east. And if you draw me all these arrows pointing to the east for different x and y values, each with length 5, then I know the wind speed is 5 miles per hour to the east everywhere, because you draw me a bunch of arrows pointing 5 miles per hour to the east. So this is the idea behind vectors. They have two quantities associated to them. They have a direction and then what's called a magnitude, right? This number tells you how long the vector is, how big the vector is. If the wind speed were like 20 miles an hour, you'd show that with a vector by making it longer. If you see a bunch of long vectors, then you know the magnitude associated, the number associated with the vector is bigger. So at its heart, vectors are not a difficult idea. What I see people getting confused with is the terminology that comes along. There's like 20 different terms you have to wade through, you have to figure out how to work with when you get into vectors. So I'm going to try to lay it all out for you and see if you can use it or not. At its heart, a vector is just a directed line segment. The length of the line segment is called the magnitude, and the way that the line segment points is called the direction. So that's what it says right here. Geometrically speaking, a vector is a directed line segment. The length of such a line segment is called the magnitude of the vector. The magnitude of the vector length of the line segment. Now, there are fundamentally two different ways, I believe, to deal with vectors. One way is geometric, where you have a bunch of pictures. You have arrows and they make right triangles, and you can add vectors geometrically. You can draw a bunch of pictures. Right? The other method is algebraically, where you don't need any pictures at all and everything's done just with symbols. So we'll talk a little bit about the geometric meaning of a vector, and then we'll talk a little bit about the algebraic meaning of a vector. So the geometric meaning has a bunch of pictures. So let me give you an example. So I drew a vector u, made it up out of nowhere. That's how amazing I am. So this new object that we're trying to wrap our head around, directed line segment. I drew you a picture of this directed line segment u. Now I put it on a grid. It clearly starts from the point 0, 1, and it goes up 1 and over 2. So let me draw that over here just for representation. Starts here, ends here. Now the arrow on a vector doesn't mean that the vector goes on forever. The arrow means it points in that direction. If I were to draw the arrow, right now the arrow is drawn pointing toward the positive x, positive y direction. If I wanted to, I could turn this vector around and draw the arrow on the other side. That would be a different vector, right? That would be like the wind changing direction 180 degrees. But in this particular guy, I put the arrow up here. The first thing I say is to draw two different representations of the vector u. You'll notice whenever I'm talking about a vector in the notes, I put a little arrow above it. That's just to differentiate between a vector and a number, right? Because a vector is more than a number. It has a direction and a magnitude associated with it. So in my notes, I put a little arrow. What the book does, the book makes your vectors boldface usually. Okay, so this is, the arrow means vector, but that's the same thing as if I would have made it boldface. But I can't do that on the board. Now to draw two different representations of u means I need to draw two other vectors that have the same magnitude in the same direction. I need to draw two directed line segments with the same length in the same direction. How can I do that?
Move it down or up.
Move it anywhere. As long as it keeps the same direction and the same length, it'll be the same vector. So what I mean is, if I start down here at 2, 0, and I go up 1 over 2, the guy that starts here and goes in this direction, that's also u. The definition of a vector, what a vector means, has nothing to do with a starting point. As long as you have the same length and you point in the same direction, you will be the same vector, no matter where you start. Put the guy down here, down 5 units, I guess. As long as he goes up 1 over 2 and points in the same direction, that's also u. Draw negative u. What do you think a negative in front of a vector is going to mean? Flips it, just like a negative radius or a negative x value. It just turns it in the exact opposite direction. So negative u, one representation would be the guy that points this way. Specifically, instead of going up 1 to the right 2, he would have to go down 1 to the left 2. Right, so a negative in front of your vector means you go in the exact opposite direction. Another way to quickly draw the opposite vector, the vector with a negative in front, is to turn the arrow on the original. So if I start from over here, and I go this direction, and put an arrow, that would be negative u. Because it's the same length, but the exact opposite direction. If I start from over here, and go to the end, but put an arrow on the other side, that would be negative. What do you think 3 times u means, right? Say 3u. Draw 3u in 2 different representations of it.
Increasing the magnitude?
Yeah, so 3 outside, 3 being multiplied by your vector is going to make it triple the size. It's just going to multiply the size of your vector by 3. Let me do this guy in green. So instead of going up 1 over 2, what do you think 3u is going to do? Up 3 over 6. It multiplies everything by 3. 1, 2, 3. 1, 2. 3u is going to look like that. And if you were to put the vector 1u, the original guy, If you were to put him head to tail, meaning if you were to go along U and then put the same thing again, and then put the same thing again, you would be able to fit 3 of them exactly. So when we do this, when we put a number out in front like this, a number times our vector, this is called scalar multiplication. There's this concept in the theory, I guess theory is kind of a big word, but there's this concept in the theory of vectors versus scalars. A scalar is just a number. It's got no direction. It's got really no meaning associated to it. Okay? A vector is a direction and a magnitude, so a length. The length of the vector is a number. But a vector is more than a scalar because it also has a direction associated to it. So vectors are somehow greater than it. They have more information than just a number. This is called scalar multiplication because I'm taking just a number and multiplying it by a vector. There are forms of vector multiplication. There are actually 2 common forms of vector multiplication, the dot product and the cross product. But we don't quite get that far. Scalar multiplication, when you multiply your vector by a number, it will always have the effect of changing the magnitude. If you multiply by 3, you triple the magnitude. If you multiply by 5, the magnitude grows by a factor of 5. What happens, you think, if you multiply by a half? Shrinks it. This guy here that only goes half the distance, that would be 1/2 u. So along with multiplying vectors by scalars, which just changes the magnitude of the vector, changes the size, you can add and subtract vectors. Okay, so this example gets at how you add and subtract vectors geometrically. So on the grid, I give you 2 vectors, u and v. U looks like it goes up 3 over 1. 1, 2, 3, 1. So here's u. V looks like it goes over 1, 2, 3, 4, 5, down 1. Here's V. Imagine walking along these vectors. Draw the vector that represents the overall distance and direction that you would walk if you first walked along u and then walked along v. So remember, vectors don't have to start at any one particular place. If you want to add vectors geometrically, you have to consider moving one of the vectors so that the start of the vector ends up at the end of the other vector. So if I wanted to add u and v, say I wanted to do u plus v, I would imagine first walking along u, which will leave me right here, but then I would walk along v starting from here. So I'm going to move v up. Starting from the end of u, I'm going to go down 1 over 5. this vector is u. This vector is v, just moved, shifted up. And this vector that goes from the origin to the end here is the vector u plus v. So this new vector has a different direction than u and a different direction than v. And it's got a different length than either u or v. Does it matter whether I go along v first and then u? Or u first and then v? Like if I wanted to add this in a different order, v plus u? What would you do?
It looks like you still get the same triangle, it's just one would not fit inside the quadrant.
Yeah. So if I wanted to do v plus u, I'd have to go this way first. V. But then, instead of keeping u starting at the origin, I would have to move u over. So u usually goes up 3 over 1. So now it would go up 1, 2, 3 over 1. So here's u. But it gets you to the same place. So in the terminology of vectors, this is called putting the vectors head to tail, or end to start. Right? To add vectors, the end of one vector has to be the start of another. And then you can add them together to figure out where you end up. How would you subtract them? Any idea?
Go the other way, starting from the euro lines.
Tail to the tail.
Yeah, so instead of, say I wanted to do u minus v. What does a minus in front of v do? Flips it the exact opposite way. Right, so minus v would go, instead of going over 5 down 1, would go left 5 up 1. So this would be minus v. Which means I can do u minus v like this. I just go out u, and then I flip v around. So, vectors are just directed line segments. And there is a geometric way to add them and a geometric way to multiply them by numbers. Right? To add vectors just means you place the start of one at the end of the other and walk along. This is your addition, this is your result. Unfortunately, that gets tedious in problems. Right? If you want to actually calculate the sum of two vectors, it would be much easier if we had a nice formula we could follow. And a nice coordinates, nice numbers to represent these vectors. So that leads us to something called a unit vector. Well, I'll tell you what a unit vector is, and then I'll call it up here. So if you want to actually put coordinates on your vectors, you use something called a unit vector. So a unit vector is any vector of magnitude 1. And there are two very helpful unit vectors that we use all the time. So one very helpful unit vector is the vector of magnitude 1 that starts from the origin and goes in the positive x direction. It doesn't have to start from the origin, but it has to go horizontally in the positive x direction. This vector is called the vector I. And then the vector that goes directly up is called the vector j. these vectors are nice because they give us some sort of standard representation of every other vector. So for example, here's a random vector v. How can I express v in terms of I and j? So v is the hypotenuse of a triangle, right? And if you think of this idea about adding vectors, you can start from the origin and add a bunch of i's, and then add a bunch of j's, and you can get v out of it. How many i's would you have to add, and how many j's would you have to add? 3 i's and 2 j's. So v is equal to 3i plus 2j. Every vector in the world that you draw in 2 dimensions, any directed line segment you draw, can be expressed as some number of i's plus some number of j's. Okay, so these are kind of your standard coordinates, your standard unit vectors to help describe any other vector that you might want to use. So on Wednesday, I will go into some examples on how to use this stuff, and then we'll do what we can in conic sections.